47, a 100-kilogram boy and a 50-kilogram girl, each holding a spring scale, pull against each other as shown in the diagram below. Okay, so boy, girl, and they each have their own scale, and the scales are connected. And the graph below shows the relationship between the magnitude of the force that the boy applies on his spring scale and time. So he's applying over the first few seconds a little more force with each passing second. Okay, and then which graph best represents the relationship between the magnitude of the force that the girl applies on her spring scale and time? So, if this guy is doing no force at 0 seconds and then 1 Newton at 1 second and 4 newtons at 1 second, 8 newtons at 2 seconds, 12 newtons at 3 seconds, and so on, then what must she be doing to match him? Now it's tempting to see that they have different masses, but their masses are already baked in to the force. Really what you need to focus on is what's happening here. If there's, you know from Newton's second law that F net equals ma, right? So if there's a net force, in other words, if he's pulling harder than her, then they will accelerate, right? If there's an F net, then there'll be an acceleration. But we know that they're pulling on each other and they're not going anywhere. Nobody's falling over or, getting pulled to the ground or anything like that. So there can be no net force. Otherwise there would be an acceleration. So for F net to equal 0, acceleration must equal 0. And what I'm getting at is that the force that he's pulling with, force of the boy, is equal and opposite to the force that she's pulling with, force of the girl. And if he's changing how much force he's pulling with over time, then she had better change to match him so that they continue to be equal. Otherwise, the system will accelerate. Somebody's going to move. Okay, so if he's going from 0 to 12 linearly over the course of 3 seconds, she's going to go from 0 to 12 linearly over the course of 3 seconds, and that corresponds to this chart. In the second chart, she's going up to 24. Again, tempting to think that she's applying more force because she's smaller and she has to make up for it, but that's not what's really happening. Her size is already cooked in to the fact that these forces have to be equal, and all these charts show is force versus time, so it's not going to be greater, and it's certainly not going to be less. Now here she's only getting up to, say, 6 newtons, and here she's just applying an even force, 12 newtons constant over time. No, if he's changing with time, she has to change with time too, so that they're always matched at every moment. So 1 is the best choice.